exploring quadratic and exponential graphs. Hopefully, we have a little feel for what quadratic graphs look like. We got a little feel for it. We weren't supposed to get too crazy in this chapter. We were just supposed to go, what is a quadratic? What does it look like? We didn't do too much here. But I'm going to compare that to something called exponential graphs, because the two of them get confused pretty easily. So my job to make sure that you have a chance to see the difference between the two. So compare the graphs of y equals x to the power of 2 and 2 to the power of x. They look very similar. The equations do. But the graphs are not very similar at all. In fact, I think that's my big moment in this lesson is to go, there's almost nothing the same about these things. Okay? Very different. And we'll show you why. And determine the meaning of 0 and negative exponents. What? That is a big goal. My job to land this thing and make you go, actually, if I do it just right, you'll be unimpressed. You won't think 0 and negative exponents are really a big deal. Ugh. Pressure's on. See what I can do. Investigate. Fold a piece of paper in half. Oh, okay. This won't translate too well in the video, but I'll try and describe what I'm doing. And you in the class can watch what I'm doing. You can also take a piece of paper and do it, or you can just watch me do it, okay? Take a piece of paper and fold it in half. Difficult? No. Yeah. It says number of folds. How many layers now? I did one fold. How many layers do you see, though, now that's folded? There's now 2 layers. Then fold it in half again. I'm using my tongue because I'm imitating my 7-year-old. Anytime he does something that's a little bit difficult with his hands, his tongue immediately comes out. How many layers? 1, 2, 3, 4. If I really fold in half, now I have 4. After 2 folds, 4. Don't read too much into it yet, okay? Don't try and make any grand conclusions. You guys are great at making the big conclusions. But this one, you're going to have to wait. There's a big conclusion coming, but you're going to have to wait. Fold it again. How many you got? 8. That's right. If you fold it up, mine's hard to count because I got the little ends on there. 1, 2, 3, 4, 5, 6, 7, 8. 8 layers after 3 folds. Fold it again. He doesn't have a piece of paper, but he said 16. He can see what's happening here. Maybe he can see in the table, or maybe he's just looking at the paper going, there's 8 over here. If I fold it and bring these 8 layers over there, that's 8 and 8. Now it's those 8 and those 8 is 16. Yes? Fifth one, 5th fold coming up here. 32. I'm looking at the side of mine and going, I don't know if I can count these. 32. But I do know it was 16 on this side. They were very stressed and brought it up. Where's Mr. Yak? I'm like, I don't care. And she's like, oh, that's fine. Yeah. There's 16 over here and 16 over there. After 5 folds, 32. I didn't count them. I just looked. I didn't look at my table. You could. I just looked and went, there's 16 layers over here. I put them together with those 16 layers. That's 32. So now, again, 32 layers. And another 32 layers. 64 layers. And whoever made up this table knew what was going to happen here. The 7th layer. Yeah. Maybe I can sort of cheat and do 7, but can you see there's no way I'm doing 8? Yeah? Nicely? I can do it in theory in my brain, but I can't actually do it. But after 7, 128. To give it away, this is called an exponential relationship. And the reason it's exponential is because the number of layers depends on how many layers you've already got. If you've got a lot of layers, you get a lot more layers. This is how rabbits work too, by the way. If you've got a couple of rabbits, they immediately become like 5 rabbits. But if you've got 20 rabbits, they become like 50 rabbits really fast. Rabbits and mice are like this. And bacteria and viruses. What's that? And flies. And coronavirus is like this. That's why things got so out of hand, is because once 64 people had coronavirus, it wasn't long before 128 had it, and things spiral out of control very, very quickly. Okay? That's all I'm going to say about that. There's a reason why things got crazy there. Anyways, it says, is this relationship quadratic? Okay, now back to your knowledge. How do we decide by looking at a table if it's quadratic? Hold on. Yes, something's got to go up by the same amount, and I'm going to not get it right here, okay? This is not correct, even though I'm going to do the math right. This goes up by 2, then up by 4, then up by 8, then up by 16, then up by 32, then up by 64. That's technically grade 9 work. That's called first differences. What we decided here is this is not linear. First differences not constant. That's not how we decide if something's quadratic, but it's on the way. If we want to know if it's quadratic, then what do? The second differences, I just do them again. I find the differences of the differences. And if that makes more sense, the first time I said that, some people freaked out. They went, what? Differences of differences? You know, and you hadn't seen it before, it sounds weird. But all I'm doing is find the differences and then find the differences of those, and look what happens. It stays the same. So, not quadratic. Second difference is not equal. I think on your practice quiz it says you got 3 choices. Is this thing linear? Is it quadratic? Or is it neither? This is one of the neither categories. It's like, no, this isn't linear. It's not quadratic. It's something else. This one's called exponential because the first differences double every time. Yeah? Later on, just to jump 2 courses ahead, we'll look at the first ratios, and they're doubling every time. That's how we know it's exponential. But we don't have to go there just yet. We just have to go, this is not quadratic. Any questions so far? Well, if I went to graph that against a quadratic, there's the graph I would get, 2 to the x. You see it goes, it went 1, then 2, 4, 8, 16, 32. It gets really big, like really fast. That's exponential growth. Exponential growth is known for growing very, very quickly. It even outgrows x squared. Think about, we look back at our table, 7 squared is only 49. Here I'm up to 128. So exponential growth, much faster growth. Anyways, there's the 2 graphs. Now notice this graph on purpose doesn't show you much of what's going on here. We got to talk about what's going on over there. We've just looked at the right-hand side for now, and we'll talk about that in a minute, why it looks like that. Because that looks weird. Anyways, let's compare. The vertex of the quadratic was 0, 0. The vertex of this one, none. It doesn't have a vertex. It doesn't have a lowest that it gets to. Axis symmetry, x equals 0. Axis symmetry of exponential, none. Just how you do this whole example to compare them and show they're not the same? Pretty much. That's pretty much the deal today. 2 to the x is a completely different graph than x squared. Maybe that would have been enough. Maybe you could have come in today and I said, listen, 2 to the x is completely different than x squared. Go home. Yeah, that's the big, big moment of the lesson. Zeros, x equals 0. There's 1 0 of a quadratic. Exponential, none. You're like, wait, it's got to eventually hit 0, doesn't it? I'm like, no, let's go the other way here. This table that I built was multiplying by 2 every time. Let's go the other way. And let's divide by 2 and see how long it takes me to get to 0. Get ready. Take 2 divided by 2. 1. Divided by 2. 0.5 or 1/2. Yeah. Divide by 2. 1/4. Divided by 2. 1/8 divided by 2. 1/16. How long can we do this for? Forever. You can keep dividing by 2 as long as you want, and it's never going to get to 0. It's always going to be a little bit, a little tiny bit. Actually, let me show you on Desmos. I can show you a great graph of this on Desmos. This is really fun. Wait till you check this out. Now get ready. I can show you this, but I can't unshow you. Once you see this, your mind might be permanently blown. Ready? There's 2 to the x. And we're going to go, when does it reach 0? So I'm going to start going left. Got to watch carefully. I'm going to start going left here. Like there. See? It hits the axis. I'm like, okay, let me zoom in a little bit. It's still not there. You go, well, keep going left, Mr. Todd. I'm like, okay, we will go left. Okay, it's got to hit it by now. No, zoom in. Look at me zooming in. Look at all the zooming I got to do. But look. Now look at the scale on the side over here, though. I'm down to a scale of 0.00005. But do you see what's going to happen? If I divide that in half, divide it in half, divide it in half. Okay, here we go. Bigger scale. X-axis, negative 5,000 up to 0. There, now I'm at negative 5,000, yes? Or negative 6,000. Zooming in, zooming in, zooming in, zooming in, zooming in, zooming in. Well, I got to zoom in farther this time. I might reach the limit of this program eventually. I've reached the limit of the program. So I'll just click on a point. Yeah, we've reached the limit of the program. I went farther than the program can handle. Let's go back left a little bit. Negative 1,000? Oh, I've put negative 10,000. Now I'm just playing around, finding the limits of the program. Okay, the program only goes down to, what does this mean? Has anyone seen this before? 2 times 10 to the negative 7. It's scientific notation. And what that means is multiply by, no, don't multiply by 10. It's got a little negative up there. We're going to talk about negatives in a second. It means divide by 10 7 times. 0.000002. Yeah. And it still doesn't meet the axis. No matter how far I go that way, it never gets to the axis. Well, that's very strange. And can blow your brain up a little bit. All that to convince you that thing doesn't have any zeros, even though it will look like it does. See, when they draw the picture in your textbook, you see it looks like it smashes right into 0. It doesn't. You got to zoom in to see it. Well, what's the last 2 things? Y-intercept. Okay, this has a y-intercept of y equals 0. And this one does have a y-intercept. It actually works out to y equals 1. But it's not clear why that is. Because it equals 1. Well, we can plug it in, right? Y equals 2 to the 0. And your calculator says 1. And your brain goes, what? Exponent 0 is 1. Well, now's the time in the lesson where I show you the most important thing. Check this out. I'm going to work it out. All on this table. I'm going to go 2 to the power of 5. And 2 to the power of 5 is 32. I wrote it all out. This is me carefully studying what exponents really mean. Hopefully that's easy. Is that easy? Yeah. Now I'm going to watch. Watch what my plan is. This is beautiful. Now I look at 2 to the power of 4. I get an answer 16. You're unimpressed. Be unimpressed by everything I'm doing except for one thing. Maybe you see what I'm about to do. 5, 4. We're going to keep going. See what's next. 2 to the power of 3. 2 times 2 times 2. You're unimpressed. You should be. 2 to the power of 2. 2 times 2. You should be unimpressed. But now things get really interesting. Like really interesting for a while. 2 to the power of 1. That means I'm multiplying by 2, but only one time. There's only one 2 there. The answer is 2. 2 to the power of 1. So an exponent of 1 means you keep it the same. Okay, you're unimpressed. Maybe you're still unimpressed. But watch this one. Every time, I keep taking a power of 2 out. The same as dividing by 2. So this next answer is 2 divided by 2, which is 1. Anything to the power of 0 has to equal 1. If that boggles your mind, the only way power of 0 actually comes up is when you take something and divide it by itself. That's how you get power of 0. That's where it comes from. And anything divided by itself is 1. So what does exponent 0 mean? Exponent 0 means you divided something by itself. That's all. That's simple. Okay, now get ready. Now I divide by 2 again. What's 1 divided by 2? I know you want it to be negative. It's just 1/2. And I know that negative, you're like, doesn't it have to be negative? No. Here's a sentence that might cause the click in your brain. Negative exponents means divide by 2 as opposed to multiply by 2. So I just divided by 2 instead. Watch this, 2 to the negative 2. What's half of a half? A quarter, which is 1 over 2 squared. All that negative exponent means is you're dividing by those things. Put them in the denominator. Best table, maybe that I'll show you all year, is to go, what do 0 exponents and negative exponents mean? Back to the lesson. Build this table of values. Okay. If you're trying to do a table of values of a exponential, go in reverse. Start with 2 to the power of 3. What's 2 to the power of 3? 2 to the power of 2. 2 to the power of 1. 2. 2 to the power of 0. New knowledge. 1. 2 to the power of negative 1. 0.5. You know the answer now, but I want you to think of it this way. This is the best way to think about it, is to go, okay, 2 to the negative 1 means 1 over 2 to the power of 1. Divide by the 2 to the power of 1. And that's how you get 1/2. 2 to the negative 2. 1 over 2 to the 2, which is 1 over 4. You're like, hold on. Stop. Wait. You're saying negative exponents means it's a positive exponent that's in the denominator. Yes, that's perfect sentence. If you get a negative exponent, it is a positive exponent that needs to be put down in the denominator. So 2 to the negative 3, who wants a shot at it? What is it going to look like? Yes, so true, 0.125, that's correct. But if you're going to write it with exponents, 1 over 2, 2 to the power of 3. So it still is 2 to the power of 3, it's just 1 over that. And you really want there to be a negative involved here, right? You're like, Where's the negative? The negative is in the dividing, because we're dividing instead of multiplying. Positive exponents mean multiply by something. Negative exponents mean divide by something. Weird. Let's try this one then. Let's do it again. 4 to the power of 3. Ooh. Anyone do that in their head? 4 to the power of 3? 64. 4 times 4 times 4 is 64. 4 to the power of 2. 4 to the power of 1. Anything to the power of 1 just stays the same. 4 to the power of 0. 1, because we're just dividing by itself. That's what exponent 0 means. Divide something by itself. Okay, let's try and do these ones in the new fancy way. 4 to the negative 1. What does the negative exponent get you to do? Divide by it. So you're dividing by the 4 to the power of 1. So the negative exponents, all it does is say, yes, you can have positive exponent, but you've got to put it down in the denominator. And 4 to the negative 2, same thing. Put it in the denominator, and I get 1/16. 4 to the negative 3, into the denominator, and I get 1 over 64. Do you see why it doesn't work like quadratics at all? It's not symmetrical at all. The same things don't happen on either side. You don't get the same numbers because you're multiplying on one side and dividing by the other. Okay. That's not easy, friends. If your brain is swimming now, you're like, what's happening? Yeah, I know, that's difficult. We're going to do a bunch of examples to make sure we got it. Do you need more time here? Write a rule for powers with exponent 0. It's always going to be 1. So I'm just going to add a couple words. Anything with exponent 0 equals 1. It represents dividing something by itself. That's the part to understand, if you really want to understand what's going on here. So let me just write that sentence too. It represents dividing something by itself. That's where 0 exponents come from. If somebody says, why would you even need a 0 exponent? 0 exponents only come from dividing something by itself. Question?
I had a question. What about 0 to the power of 0?
Oh, that's a great question. Oh my goodness. It's a great question. Zero to the power of 0. This thing's actually called indeterminate form. And what we mean by that, we don't know what to call this. We don't know what to say. Because it can't be 0 to the power of 0. 0 was divided by itself. We can't do that. And yet it's power of 0, so isn't it always 1? So this is a big mystery. Let me tell you. I'll fast forward. How many courses do I got to fast forward to tell you about this? You're in 10, right? So grade 11. Next September, for many of you. Advanced functions, next February, for most of you. Calculus. Little calculus here for you on a Wednesday. The only way 0 to 0 comes up is when the base is heading towards 0 and the exponent is also heading towards 0. That's the only way it ever comes up in calculus, where 0 to 0 would actually happen. So it's not that we would be talking about 0 to the power of 0. We'd be talking about something close to 0 to the exponent, something close to 0. Then the question is, who's going to 0 faster? Who wins the race? That's the game we'll play in calculus, and it's not nearly as difficult as it sounds to actually pull these things off. Okay? So 0 over 0 is a big problem. We'll spend, 0 to the 0 is a big problem, and we'll deal with it much later. And I'm exaggerating a little bit because it's actually 0 to the 0 actually is the second calculus course, not the first one. But so it's a long way away. It's okay if you look at that and go, ah. Okay? All we want to accomplish is anything but 0 to the power of 0 is 1. How about negative exponents? Does anyone have a handle on this? that can write a nice, succinct little rule about negative exponents that somebody can look at in their notes and go, oh, that's what I do with negative exponents? It becomes 1 over the term with exponent changed to positive. Meaning, it represents dividing by that base repeatedly. That's what's going on. But I'm not expecting that to be easy. Let's see. Some things I teach, like when I taught you vertex, I go, this is the vertex, it's the lowest point. Hopefully that's like, I get that. That's the vertex. Some things in math are like that. Some things in math like this are like, on a scale of 1 to 100, you're like a 47 when I'm done explaining. You're like, I kind of get it. And that's the best we can do without practicing more. Yeah, that's the best we can do so far. What? It represents? Yeah? Well, I think the rest are examples, right? You're like, stop talking. Just show me how to do the math. It's nice about math lessons sometimes. The second part is like, okay, let's just see if we got this or not. One at a time. How many is there? There's 9 to do, right? 8? Do you need more time to copy those sentences? Is it okay? Okay, here we go. Now we find out. How did I do? A to the power of 0. What's a to the power of 0? 1. Unless that base is 0, which it won't be until calculus much later, anything to the power of 0 is 1. It represents 8 must have got divided by itself. That's the only way we can end up here, is 8 got divided by itself. Then, just to mess you up, we throw this in here. How about negative a to the power of 0? And before I do that one, I'm going to do c, because I don't want to fool you too quickly and mess you up too quickly. So I'm going to jump ahead to c. What about negative 8 to the power of 0? No tricks. 1. I need to tell you this one is not 1. What is it? Negative 1. Here's the way you should think about it. This one, I'm going to do it in words. Sometimes the words helps people, and sometimes something I'm going to write is going to help. When we write negative 8 to the power of 0 like this in brackets, we mean negative 8 to the power of 0. And the only thing I did there was put a little space in how I said it, a little time. That's negative 8 to the power of 0. This is not that. This is, listen to how I say it, this is negative 8 to the power of 0. Yeah? Exponents go first before multiplication. So if you want, it's really like this. That's what that means, is put the exponent on first. And when I put the exponent on first, I do get 1, but meanwhile there's this negative out front making it negative. You're like, oh, that's tricky, I don't like that. Okay, off the record, I know it's on video, but off the record, just to let you know, your calculator knows what's going on. So when you're stuck on these things, just make sure you type it in. If you type with a bracket around, you'll get 1. If you don't put a bracket around, you'll get negative 1, because the 8 gets exponent 0 first. Then you multiply by the negative 1. Yeah? A and C are like, pretty easy, and B's like, okay, that I don't like. Like, I know, that's troublesome. 4 more to go. 6 to the negative 2. Who's got this? 1 over 36. She's a step ahead of me. I'm going to write it 1 over 6 to the power of 2. I'm okay with what you said, but I'm showing the extra step for people. Somebody at that moment goes, wait a minute, so negative exponents don't mean negative numbers? No, negative exponent means divide. Positive exponent means multiply. Negative exponent must mean divide. And that's how we get the 1 over 36. Let's jump over to this one. C again, not much more difficult. 1 over 36 again because you go 1 over negative 6 squared, which is 1 over 36. You guys have a G and H. My thing doesn't show G and H, but oh, I'll find it. I'll find it. Don't worry. But this one more. See, I'm getting you to juggle 3 balls here at once. Exponent laws, fractions, negative exponents, and then now I've just thrown in another negative sign in there. The negative acts afterwards. The exponent goes first. So if you want, this is negative 6 to the negative 2. The exponent's got to go first. So this is negative 1 over 6 squared. So this is negative 1 over 36. Mr. Todd, I thought you said negative exponents don't mean negative numbers. I say they don't. This is only negative because it had a negative out front. The negative exponent didn't make a negative. The negative out front made it negative. You're hurting my brain on a Thursday and I don't like it. It's only a good workout if your brain hurts afterwards. This is assigned work as if this lesson's over. But you don't have that. You got more, don't you? I'll put them right here. D. What's the first one? 2/3. To the negative 2. Oh my goodness, this is hard. This is really hard. Stick with me till the end, because maybe you see a shortcut. You got to do it once, the long way, and then maybe you see a shortcut. This would be 1 over 2/3 now to the positive exponent. You're like, fractions in fractions. Like, I know. It's okay. It'll be all right. It's going to be all right. 2/3 squared. 4, I agree with. 4/9, yeah. You're like, I am not okay with what you're doing, Mr. Todd. You've got a fraction inside a fraction. It's going to be a problem in all future grades, but I can fix the problem. I can make it look easier. Don't write it as fraction anymore. Write it as divide. Isn't that nicer? 1 divided by 4/9. How do we divide fractions? Multiply by the reciprocal. And I get 9/4. Do you see a shortcut?
Yeah. Just multiply it 4/9.
She did this, folks. I'll try and describe it on the video. She took 2 fingers, put them in the air, little sideways peace sign, and she went like this. It's the universal hand signal for flipping a fraction. She says, oh, just flip the fraction. And I agree. You can do it whenever you want. Some people do it like this. A negative exponent means flip the fraction. That's what's going to happen. And then you get there really fast. And so negative exponents on fractions doesn't have to be super hard. But they need practice, folks. These are not easy. What's your last one?
Negative 2/3.
Well, where's the negative? Inside. Who wants the shortcut? Negative exponent means flip the fraction. Negative exponent means flip the fraction. Numerator goes to the denominator. Denominator goes to the numerator. And then you can square both pieces and you're done. Easy? No. Do not let my tone of voice fool you into thinking I think this is easy. It's my job to say these things out loud in a way that makes you go, oh, I can do that. No, but not simple. Those of you who are, oh, I do my homework when I need to type people, better get in the game here. This takes a little bit of practice to knock this down.
Yep.
Yeah.